All right, in this video, we're going to do a few more examples with the ideal gas law just to get the sense of how the formula works and how to approach the problem. So let's go to this example over here. We have 10.5 grams of N2, nitrogen gas, occupies 2 liters at 125 degrees Celsius. Determine the pressure. All right, so we want to find the pressure here specifically. Let's write down what information we have. So we have a volume of 2.0 liters. We have a temperature provided to us, 125 degrees Celsius, but keep in mind we want to convert that to Kelvin. Whenever we have our temperature, we don't want those negative values, and we want that nice direct relationship. So 273.15 gives us, so we have our 125 plus our 273.15, and we get 398.15 Kelvin. And we also have, we don't have the number of moles, but we have the mass given to us. So our mass is 10.5 grams. And we can find the number of moles by doing mass over molar mass, which is the 10.5 grams, over the molar mass of N2, don't forget, which is 28.02 grams per mole, because it's not just N, it's N2. Cross out grams, so we get 10.5 divided by 10.5 divided by 28.02, and we get approximately 0.3747 moles of N2. I have more digits in my calculator. I'll just keep it in there for now. And what do we want to find? Well, we want to find the pressure. We want to find the pressure. Another thing we also have, don't forget, is our R constant, which is 8.314. And don't forget, because we were using this constant here, we're going to get pressure in kPa. If we want to find it in some other unit, we'd find it in kPa first, and then we could convert using our pressure conversion bar that we've seen before. So we know from our formula that PV is equal to nRT. And so if we want to find pressure, we just have to isolate for pressure by doing nRT over our volume, which is our number of moles, so 0.3747 moles. And there's more digits, but they're in my calculator, times the 8.314. And then remember your units for that. So it's kPa liters mole Kelvin. kPa liters per mole Kelvin times the temperature, which is 398.15 Kelvin, over the volume, which is 2.0 liters. So notice we can cancel out liters, we can cancel out Kelvin, we can cancel out moles, and what are we left with? kPa. And so that would give us approximately, so let's finish that here. We get number of moles times 8.314 times 398.15 divided by 2. We get kPa, which is approximately, if we're doing this to 2 sig figs, 620 kPa, or 6.2 times 10 to the power of 2 kPa, and you can write your therefore statement. So therefore, the pressure is approximately 620 kPa. And so the reason I knew it was kPa is because we're using this gas constant of 8.314, which has the kPa unit in there, and that's how we're getting kPa directly. Let's take a look to make sure we're on the right track. There we go. So there is our correct answer, 620 kPa. So in the previous video, we saw an example where we had to solve for n. So we rearranged our equation to get the n value. In this video, we saw we had to rearrange our equation to get the p-value because we were looking for the pressure. So in the next video coming up, we're going to do a few more examples using the ideal gas law. Again, make sure you try the questions first and then use the videos that we do to check your work.